I will talk about LP averages of the discrete Fourier transform, Salem sets, and applications. This is a joint work with Jonathan Fraser, who is also from the University of St. Andrews. I will start briefly with the introduction, then I move to basics of discrete Fourier analysis, then I'll formulate main question, then I'll explain the main approach, which is the LP averages of the discrete Fourier transform, and finally I'll show some applications of this method. Now, discrete Fourier analysis is an important tool in solving geometric and combinatorial problems in discrete setting. Perhaps its most significant application is in the resolution of Erdős-Thurn conjecture, which asserts that any subset of integers with positive upper density contains arbitrarily long arithmetic progressions. In 1953, Klaus Roth provided a partial resolution of this conjecture for arithmetic progressions of length 3 using an original technique based on discrete Fourier analysis. Over the last 20-25 years, many problems in Euclidean harmonic analysis and geometric measure theory have been formulated in the setting of vector spaces over finite fields. Notable examples include the work of Bourget and Katz-Tau, Dvir, Yosevich, Rudnev, and Wolf. The motivation for this transition from the continuous to the finite field model is that finite fields serve as a continued analog of the Euclidean case, where many technical difficulties are eliminated. And also, usually for finite field problems, you can use techniques from number theory and combinatorics. However, we need to keep in mind that this simplification comes with a trade-off. Several familiar tools from Euclidean settings are no longer available. For instance, finite fields lack an ordering, unlike R, and exhibit additional subtleties such as non-trivial spheres of radius 0, subspaces that coincide with their orthogonal complements. Throughout this talk, we let FQ denote the finite field with Q elements, where Q is the power of prime, and we use FQ star to denote non-zero elements of FQ. So once we have a finite field, we can consider n-dimensional vector space over finite field FQ, which has Q to the n elements or vectors. By character, we mean any group homomorphism from additive group FQ to a multiplicative group of complex numbers on the unit circle. And we know that the mapping which sends everything to 1 is also a character, so it's called the trivial character. Now we need to define the main object of the discrete Fourier analysis, which is a Fourier transform. If we have a function from Fqn to C, its Fourier transform is a function which is also from Fqn to C, which is defined in the following way. So it's basically sum of characters with some weights. And here, chi is a non-trivial character. So the specific role of non-trivial character does not play an important role in what follows, and we can fix one particular choice throughout. And here, C.x is a standard dot product on Fqn. So the following formula is fundamental, and it's known as Plancherel's theorem. So it relates the L2 norm of a function and L2 norm of the Fourier transform. If we have a set in Fqn, we define Ex to be the indicator function. So it's a 0, 1 function. It's 1 if x belongs to E and 0 otherwise. And if we apply Plancherel's theorem to Ex, we obtain the following identity. The right-hand side is Q to the n, because we'll get Q to the n summation of L2 norm of the indicator function, but indicator function is a 0, 1 function, so its square is equal to itself, so it should be equal to Q to the n times E. So let's ask the following question. What can we learn from Fourier transform of E? First of all, we see that for every frequency, we have this inequality. And by Plancherel theorem, we have this equality, and we have this inequality. The first term in the inequality comes from 0 frequency, and the second term from non-zero frequencies. If we suppose that the set E is not too dense, let's say size of E is at most C times Q to the N, for some C between 0 and 1, then it's not difficult to show that we have this inequality, meaning that the largest non-zero Fourier coefficient is bigger than square root of size E, but less than size of E. And we can ask the following natural question: do we expect the largest non-zero Fourier coefficient to be close to the lower bound or upper bound? In fact, both cases are possible, and precisely where it lies in this range tells us a lot about the structure of the set E. If the largest non-zero Fourier coefficient is small, meaning that it's close to square root of size E, this indicates that the Fourier transform has undergone significant cancellation, and therefore E is rather unstructured or almost random. If the largest non-zero Fourier coefficient is large, meaning it's close to the size of E, this indicates that the Fourier transform has not undergone much cancellation, at least for some non-zero frequency, and there should be a good reason for this, such as E being highly structured in a way that it prevents cancellation. In discrete Fourier analysis, a set E is called Salem set if its largest non-zero Fourier coefficient has the following decay. Such sets should be regarded as optimal from a Fourier analytic point of view. Our main question is the following. Suppose E is unstructured or random, but not sufficiently to be a Salem set. What can we say about the set E? For example, can we use this bound to derive some combinatorial or geometric conclusion? Alternatively, can we replace L infinity norm by some suitable LP averages? And this is a novel approach, and we will explore it in greater depth for the remainder of the talk. But first of all, we need to introduce the concept of LP averages of the Fourier transform. The definition is the following. If E is a subset of FQN and P is a parameter between 1 and infinity, we define the P norm of Fourier transform in the following way. If P is finite, the P norm is defined as the sum. Because of technicalities, we remove zero frequency. And when P is equal to infinity, infinity norm is defined as the L infinity norm of the Fourier transform. Now we need to introduce the important definition, the definition of the PS Salem set. If E is a subset of FQN and we have two parameters P from 1 to infinity and S from 0 to 1, we say that the set E is a PS Salem set if the P norm of the Fourier transform has the following decay. And this symbol means there is a constant depending only on P and S. So we observe that being infinity 1/2 Salem set is equivalent to being a Salem set in the usual sense, and therefore it's a P1/2 Salem set for every P between 1 and infinity because of the monotonicity of the P norm. We can define the sphere of radius R in the following way, and one can show that spheres of non-zero radius is a Salem set. However, a sphere of zero radius is an interesting object in finite fields because, for example, when dimension is at least 3 is odd, one can show that the size of the zero sphere is large. However, when n is equal to 2 and minus 1 is not a quadratic square, zero sphere is trivial. Building on this approach, where we consider LP averages of the discrete Fourier transform instead of its maximum, we obtain a number of interesting applications. Applications are in sum sets, exceptional projections in FQN, incidences in FQN via Fourier analysis, Fourier restriction problem, and Mockenhaupt and Tao, they introduced the Fourier restriction problem, and it turns out using our approach, we can improve Mockenhaupt Tao in many ranges. So first of all, let's start with sum sets. Many problems in additive combinatorics and additive number theory, they revolve around the study of sum sets of specific sets A and B. The most famous sum set is probably Lagrange four square theorem. Given non-empty subsets A, B in FQN, the sum set is defined in the following way. And the key problem is to relate the size of some set to size of individual sets. So clearly we have the following bounds, and we observe that this bounds, they cannot be improved in general unless we have some specific conditions on the sets A and B. Of particular interest is determining under what conditions the bound in 5 can be sharpened. For example, establishing growth of the form of this form would be very nice. In the next result, we can show that using LP averages, we can do this. If A is a 4S Salem set, then the size of A plus A is at least minimum between Q and N, and size of A raised to the 4S. In particular, if S is 1/2, then we have this, and it yields optimal additive growth. Moreover, if S is bigger than 1/4, we obtain an improvement over the trivial lower bound. Now we will move to the next application. It's exceptional projection. Martian projection theorem is a celebrated theorem in fractal geometry, and it says that if we have a Borel set, the Hausdorff dimension of the orthogonal projection of this set onto almost all k-dimensional subspaces is this. And due to work of Mattila, Peres, Schlag, we have this refinement of Martian theorem. And one can consider Martian projection theorem in FQN, and the appropriate analog is the following. Here, GKN denotes the set of all k-dimensional linear subspaces of FQN, and pi VE is a projection onto the subspace. And we want to emphasize that GKN is directly related to the Gaussian binomial coefficient, which is defined in the following way. Since we care about the case when Q is large, it's not difficult to show that the Q binomial coefficient is asymptotic to Q to the K times N minus K when Q goes to infinity. And if E is a subset of Rn and V is a subspace of Rn, we know that in continuous case, the projection is defined in the following way. But we cannot define projection in FQN in the same way because of this interesting example. It turns out, if you consider this subset, which consists of 4 vectors, it's not difficult to show that this is a subspace of F24. And it's also not difficult to show that S is equal to its orthogonal complement. So in finite fields, this is not true. I mean, you cannot write the whole space as a subspace direct sum orthogonal complement. And we also have to define projection in this way. So projection of E onto subspace V is the coset of all orthogonal complements which intersect E. And we are interested in the exceptional set, which is this. And the case of interest when U is small, because otherwise the size of the exceptional set is roughly Q to the K N minus K. So we are interested in the case when U is small. And we prove the following result. If P from 2 to infinity and S from 0 to 1, and E is a non-empty PS Salem set, if U is not too large, then we have the upper bound for the exceptional set. And the fact that the upper bound depends on P allows one to optimize it by choosing the best P from the range. And this gives this theorem significant flexibility because you can take P and S to be 2 and 1/2, because every set is a 2 1/2 Salem set because of Plancherel's. And following Chen's argument, we obtain Martian projection theorem in full generality. And this result generalizes Chen's result to the case of non-prime fields and also recovers a recent result by Bright and Gunn. This is a list of references. And thank you very much for your attention.